So today we are going to study about Fourier analysis. And there is some part left in ordinary differential equation. We will do that later after the Fourier analysis. Okay. So we are going to do Fourier analysis today. Now, Fourier analysis will have three parts. One is Fourier series. Second one is Fourier integral. And third one is Fourier transform. So in Fourier series, we will try to express periodic functions in terms of Fourier series, and I'll tell you what is Fourier series. So it is basically a series of sine and cosine terms summed up to, I mean, there are infinite terms in the series, but every term is in terms of sine and cosine functions. So, and then, but we can extend the concept of Fourier series from periodic functions to non-periodic functions as well. So there comes the concept of Fourier integrals. And then Fourier transforms are actually used to extract frequencies from particular signals. So let's say you have a voice signal or speech signal. All those signals are in terms of time versus voltage, right? Because even a mic is kind of a transducer converting our voice into some kind of electrical voltage. So, and similarly noise also, if some noise is coming. So those signals may have some dominant frequencies that we would like to extract. So let's say a signal is there. In that signal, there may be 10 dominant frequencies. Although the signal will look very haphazard, so it may be very random, but still we can extract which frequencies are dominant. So for that, we will use Fourier transform. So let me start with Fourier series. So before that, I would like to talk about periodic functions. So what are periodic functions? Obviously, which repeats after a certain period of time. Now, my question is, are periodic functions always continuous? Yeah, tell me. Yes, are periodic functions always continuous? No, because you can, the simple example is a function 10x. So if you plot 10x, so it is a periodic function, but it is not continuous. It is not defined at x is equal to pi by 2 or odd multiples of pi by 2. So because at those points, it is either an infinity or minus infinity. So they may not be continuous, but it will repeat after a certain interval. So periodic functions are such that f of x plus p will be equal to f of x. Means if you are an x-axis and if you add a period to the x-axis, then you will get the same value because it is repeating. So where p is the period of the periodic function, and we will say that f of x is defined for all x except some points. So at some points, it may not be defined as well. So example is 10x. It is periodic function. But 10x is not defined. at, let's say, x is equal to plus minus pi by 2 or plus minus 3 pi by 2 and so on. But it is still periodic. So here p is the period of the function after which it will repeat, right? And so if let's say omega is the period of the function, then 2 omega will also be a period. What I want to say is, let's say we plot y is equal to sine x. It will start from 0 and obviously at pi by 2 it will be 1 and then it will be like this, right? 0, pi, pi, and this is 1 and this is minus 1. And then it will repeat, right? So, and this point will be 4 pi. So if 2 pi is the period of the function, 4 pi multiples of the period will also be period, right? Because if 2 pi is the period of function, so 4 pi will also be a period because it is going to repeat after every 4 pi as well. It is going to repeat after every 8 pi as well. Because in 4 pi there are 2 pi, 2 times 2 pi, right? In 8 pi there are 4 times 2 pi. So anyway, it is going to repeat after 4 pi as well, after each 4 pi as well, and it is going to repeat after each 8 pi as well. It means 0 to 4 pi will look same as compared to 4 pi to 8 pi. So similarly, 0 to 8 pi will look same as compared to 8 pi to 16 pi. But we will be interested in the fundamental period. So fundamental period is the lowest value of the period. So the fundamental period of sine x will be 2 pi. So let me just write here fundamental period. Lowest possible period. Okay. So now we will go to, and 10x obviously has a, what is the period of 10x? Can you tell me? Is anyone? So have you forgotten these functions? Yes, quickly tell me what is the period of 10x? You can write in the chat. So it will be pi. So because it will repeat from minus pi by 2 to, yes, correct. So uh, so the fundamental period is lowest possible period. So now let me talk about Fourier series. The Fourier series is used to approximate periodic functions using sine and cosine forms. Or we can say that sine and cosine terms. So if I write, so it will look something like this. So if let's say if you have any periodic function f of x, so you can express that function in the form of a0 plus summation n is equal to 1 to infinity an cos n pi x by l plus bn sine n pi x by l, where n is a positive integer, right? And this series Uh, so the overall period, let's find out the period of this series. So since sine x has a period of 2 pi, what is the period of sine 2x? So what I want to say is, let's say sine x has a period of 2 pi. So what is the period of fundamental period of sine 2x? So it will be pi only, right? Because if you substitute pi here at the place of x, it will be 2 pi. So, and if I add both of these functions, sine x plus sine 2x, so what is the period of this addition? So the period of this addition will be 2 pi only, because we cannot go to the lowest period, because if we say that the period is pi, but sine x will not repeat after pi. So we'll have to go to the largest possible period of the term that is present in the summation. So the period will be 2 pi. Similarly, if we want to find the period of this series, so the largest possible term that we will get when we will substitute n is equal to 1. So because otherwise it will be 2 n is equal to 1 will be pi x by l, otherwise it will be 2 pi x by l, 3 pi x by l. So the fundamental period will keep on decreasing. So okay, and now the fundamental, if we take n is equal to 1, so pi x by l should be equal to 2 pi, because that is the, if we take this total thing as an argument, so n pi x by l should approach to 2 pi, only then first period will come, right? So I'm just writing pi x by l is equal to 2 pi, right? So then x will be how much? X will be 2l, and that is the period of this series, because period will always be in terms of x. So we say that then period of this series will be 2l above Fourier series. So here, and this is the this is the periodic function, and we are expressing this periodic function in terms of summation of these terms, and all these terms combined together have a period of 2l. Okay, because if you substitute 2l here, x is equal to 2l, so you will get an cos 2n pi x. Um, yeah, so if you substitute x equal to 2l, so you will get an cos 2n pi plus bn sin 2n pi. And if you substitute n is equal to 1, so you'll get cos 2 pi plus sin 2 pi. Anyway, so the period will come out to be 2 pi only, because these two terms have the same angle. Angles are not different, right? So two terms will with same angle will give you the same period. So now this a0, an, so a0, an and bn, so these are known as Fourier coefficients. And how to determine this Fourier coefficients, I'll tell you. But first of all, let me write what is the expression of these Fourier coefficients. So a0 is given by, so here I will write Fourier coefficients a0, a1, a0, an and bn are given by Euler's formula. And let me write what is the expression of Euler's formula. So a0 will be given by 1 by 2l minus l to l f of x dx. And then a1 will be given by an, not a1. And that is 1 by l minus l to l f of x cos n pi x by l into dx. And n will be 1, 2, and so on. And similarly, bn is given by 1 by l minus l to l f of x sine n pi x by l, right? And dx. and similarly n will go from 1, 2, and so on. So these all three combined together are known as Euler's formula. So now f of x will be known to you, it will be some periodic function. We will solve one problem as well, then we will see how to obtain these Fourier coefficients. So now we have this Fourier series, and we can obtain these Fourier coefficients using this formula. Now the question arises, we had Taylor series as well. We used to express the functions in, so sin x, cosine x, we have expressed using Taylor series. But Taylor series converts any kind of function into polynomial functions, and those are not periodic. So for periodic functions, Fourier series are better compared to Taylor series. Better approximations of periodic functions can be given by Fourier series compared to Taylor series. And we can also say that for some functions, Taylor series will not be able to, for some periodic functions, Taylor series will not be able to give a very nice expansion, polynomial expansion, because polynomial expansions are non-periodic in nature. So let me just tell you how to obtain these Fourier coefficients. Before that, so to obtain these Fourier coefficients, we utilize orthogonality of the trigonometric functions. So what do we mean by orthogonality of the trigonometric functions? So when two things are orthogonal or perpendicular, let's say, then their dot product is zero, right? So similarly, we extend this concept of orthogonality from the dot product of two vectors, two perpendicular vectors, to any terms. So here orthogonality of a trigonometric function means we are going to multiply two functions and their integration is going to be zero. Okay. So still there is a multiplication of two functions, and then it somehow will go to zero. So let's see how it will go to zero. So here we are going to utilize the orthogonality of trigonometric functions. So we will just call it orthogonality relations. So there are three orthogonality relations. First one is minus pi to pi cosine of nv and cosine of mv dv. V is a variable, is equal to 0 when n is not equal to m. And obviously n and m are integers. And the second orthogonality relation is, so if you see here, we are multiplying two functions. N is not equal to m, so these are two functions, and therefore their multiplication is going to 0. So this is one of orthogonality relation. And then again minus pi to pi sine nv and cosine mv dv. That will also go to 0 when n is not equal to m. And then we have the third one, which is minus pi to pi. Just let me correct it. Here it will be sine mv. Okay. So in the last we have sine nv and cosine mv. So these two are different functions, sine and cosine. So this will be 0 irrespective of n not equal to m or n equal to m. It doesn't matter for it, for the third relation. So you can actually conceptually understand this, that if n becomes equal to n, then these two become same functions, then same functions multiplied together will not give 0 always, as per that dot product, right? So for that dot product to be 0, two vectors must be perpendicular. So here and when n is not equal to m, then only it will be two different functions. Here also when n is not equal to m, then only it will be two different functions. But here these are already different functions, sine and cosine, right? So n can be equal to m. And it's very easy to prove them. So let me just quickly do that. So I'm just doing the proof of orthogonality relations. So minus pi to pi. So let's prove the first one, cosine nv and cosine mv. Then other ones you can prove on your own. So cosine nv and cosine mv we are going to prove. So for that I am going to use the formula. So if you would have studied, so we have the formula cos a plus b. So that is nothing but cos a cos b plus sin a sin b. And then we have cos a minus b, which is here minus will come. So cos a minus b is cos a cos b plus sin a sin b, right? So now we have if you add these two terms, so you will get cosine a plus b plus cosine a minus b. So you will get twice of, because sin a sin b will get cancelled, so you will get twice of cosine a and cosine b, right? And if you multiply the first term with minus, so minus of cosine a plus b, and then you add cosine of a minus b to it. So this minus cosine a cosine b and cosine a cosine b will get cancelled, and these two terms will add up. So finally you will get twice of sin a sin b. So we are going to use this. So here we have multiplication of cosine to cosines. So we will use this formula here. So we say that cosine nv and cosine mv equal to cosine n plus mv plus cosine n minus mv and half. This two will come to the left hand side. So then we can write this integral as half of minus pi to pi cosine n plus mv plus cosine n minus mv, and obviously n is not equal to m, right? And we have dv here, and n is not equal to m. Okay, here also n was not equal to m. Anyway, so then you know what is the integral of cosine n plus mv. And anyway, whatever it is, so here minus pi to pi is a fundamental period of cosine. So minus pi to pi, what I want to say is you will cover a full curve of cosine. So area below the x-axis will be equal to area above the x-axis. So that's why this integral will go to 0. Anyway, this is the graphical interpretation I'm telling you with mathematics as well. So cosine n plus mv integral will be sine n plus mv divided by n plus m, and it is going from minus pi to pi, and then plus we have cosine of so integral of cosine n minus 1 n minus m will be sine n minus mb over n minus m, right? And it will go from minus pi to pi. And you know that if you substitute pi at the place of v, so sine some integer times pi will be 0 and minus pi will also be 0. So all these terms will go to 0. So that's why you will get 0. So that's how we prove that this integral is equal to 0. Similarly, to prove the second integral, you can just utilize this formula. You will get this in this term, and again after integrating it will convert into sine, and sine minus pi to pi will go to 0. And for the third one, so for to prove the third part, you can use another formula, which is you have to use the sine formula. So sine a plus b is equal to sine a cos b plus cos a sine b, and sine a minus b equal to sine a cos b minus cos a sine b, right? So what you have to get is you have to get sine and cosine. So um, you can just add these two terms. So if you add, you will get sine a plus b plus sine a minus b is equal to twice of sine a plus b. because cosine sine will get cancelled, and then you can use this formula here, sine nv cos mv, so that will be equal to sine n plus mv plus sine n minus mv, and if you integrate, it will go to 0. Uh, so these are orthogonality relations, and we have proved how these are derived, and we will use this in orthogonality relations in finding the expression of this an a0 an and bn Fourier coefficients. So let's do that. So finally, let me just write the Fourier series again. So this was our Fourier series f of x is equal to a0 plus n is equal to 1 to infinity an cosine of n pi x by l plus bn sine of n pi x by l. Please stop me in between if you have any doubts, okay? So firstly, we need to find a0. So for a0, if you see from here, we have integrated our function from minus L to L, right? This one. So let's do that. So if we integrate this series from minus 1 to L, minus 1 to 1, so this was for first uh, coefficient a0, how to find a0. So we will integrate our function from minus L to L. So if we do that, minus L to L, and 2L is our period of this series, or of this periodic function also. 2L is the period. Period will not change. Left hand side period should be equal to the right hand side period. I mean the fundamental period. So it will be a0 minus L to L and dx, right? Plus sigma n is equal to 1 to infinity. And then we have an, and we will integrate minus L to L cosine of n pi x by L dx, plus we will integrate bn minus L to L sine of n pi x by L into dx, right? And then we close the bracket here. So I'm just solving the right hand side. So finally we will get, so a0, so here you will get a0 and integral of dx will be x, and integrated from minus 1 to L. Minus L to L will give you 2L. So here you will get a times 2L. So this expression will be equal to this expression here. Plus, hope you have not forgotten the integration, and it's very easy integration. Fourier series and all those things are not very difficult. So if you integrate this, how to integrate this cosine pi x by. So let me just put it this way. So an, so how I'm putting is, let's say we have two more terms, this term plus this term. Okay. So the first term is this one, cosine 1, and the second term is sine 1. So let's first solve this integral here. Okay. So if I solve this integral, so I'll be solving minus L to L cosine of n pi x by L into dx, right? So I'm just doing some kind of substitution. So let's put uh, pi x by L equal to V, okay? Because I want to convert this in terms of cosine of NV, and I want to apply some orthogonality relation if it is possible. So let's convert this into in terms of cosine of NV. I'm putting pi x by L is equal to V, right? So then x will be equal to VL by pi, right? And from here we can say that dx is equal to dvl by pi, right? Now, yeah, so let's just put this, and the limits also will change. So whenever x is minus L, what will be V? So V will be a minus pi, right? When x is minus L. So then our limits will now go from minus pi to pi, and cosine of n into V we will have, and dx will be equal to dv, and L by pi will come here. Now if you integrate this one, so you will get L by pi minus pi to pi. So integral of cosine of nv is sine of nv divided by n, right? And if you do that, minus pi to pi, so that will be 0, right? So it means it doesn't matter what is the value of your n, this term is going to be 0, this integral. So it means this whole thing will go to 0. Now let's see what happens to this sine n pi x by L. So we have the second integral minus L to L sine of n pi x by L. Similarly, if we substitute pi x by L equal to v, so we will get minus pi to pi L by pi sine nv dx, right? So yeah, so finally if you integrate, so you'll get L by pi, integration of sine nv is minus of cosine nv divided by n, and it will, you have to evaluate at minus pi and pi. So if you do that, so L over pi and minus of cosine n pi, and then minus minus plus will be cosine of minus n pi, right? So it will cosine of minus x is cosine of x only, so you will get here L by pi minus of cosine n pi plus of cosine n pi, right? So again it will go to 0. So finally this term will also go to 0 and this term will also go to 0. So you will be left with only this term. So here also I'm putting here this will be 0 and this will also be 0, irrespective of the value of n. Finally, what you have got is minus L to L f of x dx is equal to a0 into 2L. So a0 will be 1 by 2L minus L to L f of x dx. And indeed that was the expression of a0, right? So we have derived the Euler formula for a0, and now similarly we'll derive for an and bn. I'll derive for an and then you can derive on your own for bn. So okay, but for an, what we had here, so for an we multiplied this function with cos n pi x by L, right? And we integrated from minus L to L. So let's do that. So we will multiply our periodic function with cos n pi x by L. So let's derive an. So for an, what you have to do is you have to multiply your function with cos n pi x by L. So instead of multiplying with cos n pi, let me just first multiply with cos m pi x by L, and later I'll prove that n is equal to m. So I'm just first multiplying with cos m pi x by L. So cosine of m pi x by L, right? And I have to integrate from minus L to L and dx. So what this expression will be equal to? So f of x was equal to a0, and a0 now will be multiplied with this integral minus L to L cosine m pi x by L dx, right? Plus I had this term here, that sigma n is equal to 1 to infinity, and here an was there, and then I have minus n L to L, and in the Fourier series I have cos n pi x by L, right? And I have multiplied this whole series with cos m pi x by L, so that also will come here. And then dx, then I have the sine term plus bn minus L to L. Again here cos m pi x by L, because I have multiplied my whole series. So yeah, so in Fourier's series, sine n pi x by L is present. So I'll write first that sine n pi x by L, and I have multiplied this with cos m pi x by L and then dx, right? Okay. So finally, you have this expression, and let's solve this. So let's solve the first one. So I'm calling this integral as the first integral, this integral as the second integral, and this integral as the third integral. Okay. So let's first solve the first integral. So first integral is nothing a0 minus L to L. Not a0 also I'm not solving, I'm just solving the integral. So minus n to L to L cos m pi x by L dx. I'm just directly integrating. So if you integrate, and obviously the period is 2L of this whole thing. So this integration will be sine m pi x by L divided by m pi by L, right? And this will go from, I have not substituted as v, we can also do that. We can put pi x by L equal to v. So everything will transform as we have done before. But anyway, so I want to show you that we can do this way as well. So it will be L by m pi. And if you substitute L here, so you will get m pi, and sine m pi will be 0. It doesn't depend the value of m. So that will be 0 plus, sorry, minus, and then again you put minus L, so you'll get sine of minus m pi. That will also be 0. So this first term will go to 0. Okay, first integral. So that's why this whole term will also go to 0. Now let's evaluate the second integral. Second integral is minus L to L cos n pi x by L cos m pi x by L. So minus L to L cos n pi x by L and dx, right? So now let's just integrate this. So here I want to substitute. So you substitute pi x by L is equal to v. So you will get x is equal to L VL by pi, and dx is equal to dvl by pi. And you do all those things, so you'll get minus pi to pi, L by pi here, cosine of nv and cosine of mv, right? But here n can be equal to m or cannot be equal to m, because we are running a series. And if you see here, um, n is going from 1 to infinity, and m is also a positive integer. So at some point of time, there will be a single term where n will be equal to m, right? Because n will go like 1, 2, 3, 4, 5, 6, and let's say m is 10. So n will be 10, right? Because at in a single in one term, at least one term, n will be 10, because n is going from 1 to infinity. So what I want to say here, that there can be two possibilities. So if n is not equal to m, so let's explore these two possibilities. So this is equal to 0 if n is not equal to m, right? By orthogonality relations. Cosine of nb, cosine of mv minus pi to pi, that is 0. But if n is equal to m, right? N is equal to m. So this relation will turn into cosine square nv, right? L by pi minus pi to pi d, right? I'm writing dx, right? Because this n is equal to m, so this will also be cosine of nv, and this will be cosine square nv. And if you know this formula, so we have cosine of 2 theta is equal to 2 cosine square theta minus 1, and cosine square theta, that's why we can write as 1 plus cos 2 theta by 2, right? If you remember this formula, we can do that. So similarly, cosine square nv can be written as 1 plus cosine of 2 nv divided by 2 minus pi to pi dv, right? So if you solve this, L by pi minus pi to pi. So the first one will be just I can say 1 by 2 and dv, and the second one will be L by 2 pi minus pi to pi cosine of 2n. Yeah. The first one, so the first term that you will get from here, so this will be nothing but 2 pi, and it will get cancelled. So finally you will get L here, I think. Yeah. And the next term will be 0. So you get answer as L. This is 0, you can just say see, because its integration will be sine 2nv by 2n, and sine of 2n pi into n minus pi will be 0. That's why this will go to 0. Okay. So finally, you will get, let me just see that. So yeah, so you'll get L here. So what you will be left with here is, when n is going from 1 to infinity, all the terms will be 0. Only a single term when n is equal to m will be non-zero. And in that case, you will get an into L, right? So this whole thing, infinite summation of the terms, will shrink to only one term, that is an multiplied by L. And then this term will be 0 because here sine is multiplied with cosine. And I told you that in orthogonality relations, when we have, obviously here when you substitute pi x by L equal to v, so it will convert into minus pi to pi sine nb and cosine mb. And this third term will go to 0 because these two are two different functions. And in orthogonality relations, I told you that um, if we have sine and cosine, then it doesn't matter if n is equal to m or n is not equal to m. For both the cases, it will be 0. The third term anyway will be 0. So finally, what we have got is this whole thing will be equal to an into L, right? So let me just write here. So minus L to L and f of x cosine of, although I multiplied with cosine of m pi x by L, but now I'm writing n pi x by L because m is equal to n. Only in the case where m is equal to n, this term is non-zero, right? So here also, this, I mean, n is equal to m or m is equal to n is the same thing. So here also m will be equal to n. So I'm just writing it here like cosine n pi x by L dx, and that is equal to an into L. So finally, you will get the expression of an, so which is 1 by L minus L to L f of x cosine n pi x by L into dx, right? So you will get the expression of an, which is the same expression that we have written here. Okay. Now, before bn, you can do the same thing. You just multiply the series with sine n pi x by L, and you will see that the first term will go to 0, and the second term will also go to 0 because it will be multiplication of cosine and sine, and the third term will be equal to L, as we have done, and then you will get bn is equal to 1 by L. This is for n is equal to m. For only one case, n is equal to m, that third term will be equal to L, and then you will get the expression of bn. Okay. Same way you have to do that. So now we have Fourier series, we have Fourier coefficient, we have orthogonality relations and proof of all of them. So let's now do the question. I'm taking a periodic function, and we will try to find out the Fourier coefficients for that periodic function, and we will see that how Fourier series approximate that periodic function. Okay. But let's take a break of 4 minutes. It's how much time is there? Here it is. Anyway, we will take a break of 4 minutes and we will resume the class after 4 minutes. Okay. Meanwhile, you can ask if you have any questions. We have 2 minutes left. Then we will resume the class. So everybody has understood. Nobody has any questions. You are you people are very smart actually, I think, because you understand at the first go and nobody ask any questions. Okay, that's a good sign. But I'm assuming that if you people have understood, sometime it happens that it's an online class and you have joined and you're sitting somewhere else. Okay, anyway, so let me just do this. So I'm writing a question here. So you have to find the Fourier coefficients of the periodic function f of x, and f of x is equal to minus k if x is minus pi to 0, and it is k if x is 0 to pi. Okay, and it is given that this is the period of the function is 2 pi, which is f of x plus 2 pi is equal to f of x. So we have p is equal to 2l is equal to 2 pi, right? It means L will be pi in our Fourier series because period was 2L. So now let me plot the graph of this function. So let's say here we have f of x and here we have x. So let's say x is here it is pi, and here it is minus pi. So at minus pi, it is minus pi to 0, it is minus k. So let's say this is minus k. And 0 to pi, it is k. Let's say this is k, and this is minus k. And then it repeats. So then it will be like this, right? And repeat in this way. So if this is pi, so this will be 2 pi, and this will be 3 pi. Right? So if at 0 to pi it is k, then in the next cycle it will be minus k, and one half cycle will be a is not 0. Yeah, in which case are you telling? In this question? Yes, in this, yeah, so in this question, first term will be 0. Yes, correct. You're right. So I'm just telling you, drawing the function as of now. Yeah, so you can actually derive a0, a and bn. So a0 will come out to be 0. So we will do that, but I want to tell you the significance of this kind of function. So this kind of functions are used for so external forces acting on mechanical systems can be approximated by this kind of function. So sometimes, let's say, if I tell you from my experience, so if we have an internal combustion engine in your vehicles, so at the top of the engine there is a camshaft and there is a valve. So that camshaft presses that valve, and then the valve goes down and the air and fuel comes in the cylinder of that engine. So when that valve rotates, so sorry, the camshaft rotates and valve is kind of a linear system. Here there is a camshaft. So when camshaft will touch this valve, it will go down. So the force exerted by camshaft on the valve will be periodic force. And it's somehow, although it is not completely rectangular, so it's not completely rectangular, it somehow comes like this. Okay, but we can approximate that force using this rectangular signals. So in those cases, these kind of functions appear. So these kind of functions appear in external forces acting on mechanical systems or electromotive forces also in electrical circuits. Maybe you would have heard of this in electrical circuits also. Some electrical circuits you will see this kind of waveforms or forces. And let me just write here the importance of these forces. This kind of signal. So this kind of signal appears when external forces external forces acting on mechanical systems can be approximated by this function, this periodic function. And this is also electromotive forces in electrical circuits. So those kind of forces can be approximated by this kind of periodic functions. So yeah, let's find out the Fourier coefficients. Somebody was telling A0 is coming out to be 0. Let's see that. So A0 was 1 by 2L minus L2L f of x dx, right? So, and we know that L is pi here in our case. So 1 by 2 pi minus pi to pi f of x dx. So let's see that. So 1 by 2 pi, so we'll have to split, so minus pi to 0. So minus pi to 0 our function will be minus k dx. And then 1 by 2 pi, we have 0 to pi and our function will be k dx, right? So if you solve this, it will be 0, no? Because um, so if you solve this will be 0. Because here you will get minus kx. So here you will get minus k pi and here you will get k pi. So it will be 0. Okay. Now let's find out an minus L to L f of x cos n pi x by L dx, right? This was our an, and our L is, yes, please find this an. So L is pi, because here we know that the period is uh, 2 pi and our period in the Fourier series was 2L. So L is pi here. So minus pi to, and then we have f of x cosine of. Can someone tell me what will be the value of an? Yes. Odd function, so an is 0. Uh, an will not be 0 because let's see. Okay. So 1 by L minus pi to pi minus pi to 0. Firstly, we'll go for minus pi to 0. So then we have here minus k cosine of n pi x by L dx. And then we have, just keeping this 1 by L common. So then we have this k 0 to pi, because f of x is k when we are going from 0 to pi, and cosine of n pi x by L. So let's solve this. And you are right that it will be 0 because it is a odd function, but I just wanted to prove it. Okay. So anyway, so 1 by pi, and because L is pi, so I'm just writing. So I think I should substitute L is equal to pi here itself. Let me not drag all this. So picture will be clear if we substitute here itself. So if we substitute here itself, so if you substitute L is equal to pi, what you will get? Cos of nx, right? Then it becomes very simple. Yeah. Now you can easily integrate. So finally you will get 1 by pi minus k minus pi to 0 cosine of nx dx plus 0 to pi k cosine of nx dx. You will get 1 over pi, and minus k will come out, and obviously someone was telling it is an odd function. So odd functions have equal area over, I mean, below and above the x-axis, so that's why they give 0 answer. So that is true, but it is a piecewise function. So firstly, you should actually split it into pieces and then you can solve it. Anyway, so here we have cosine of nx, so its integral will be sine x by n, and then we have a times sine of nx by n. Okay. So both cases you will get 0 because sine 0 is 0, sine pi is also 0. So you will get 0. Now tell me the value of bn. What will be the value of bn? So bn will be again 1 by L minus L to L f of x sine n pi x by L, right? Yes. Can someone tell me what is bn? Yes, Vakas. You have told me a0, an, and can you tell me now what is bn? So let's substitute here. So you'll get 1 over pi, because L is pi, minus pi to pi f of x sine nx, right? Because L is pi. So what we will get? 1 over pi. Um, if you do that, so you'll get minus of k sine of nx dx minus pi to 0, and then you will get 0 to pi k sine, because 0 to pi our function is k, right? Now let's solve this. So 1 over pi minus k, and this integral of sine nx will be minus of cosine nx by n, right? So you will get minus minus plus, so you will get k cosine of nx by n here, and it is going from minus pi to 0, plus here you will get minus k cosine of nx by n, and here you're going from 0 to pi. and okay, so you will get 1 over pi. Quickly, we will get k by n outside, right? And cosine of 0 minus cosine of minus n pi, right? This is the first term, and plus k by n will also be here, and then minus of cosine n pi and plus of cosine 0 finally. So you can take out k by n pi as common. So k by n pi will be outside, and 2 also will be outside because cosine of 0 plus cosine of 0 will be 1. So that will be 2, and these two terms will also add. So 2 also, so it will be 2k by n pi and 1 plus, let me just see. I think these two will get cancelled now. Just wait a minute. No, so yeah. So you'll get minus of cosine of n pi, right? Because this cos of minus theta is cos theta only, so minus of cos n pi and minus of cos n pi, so it will be twice of cos n pi. So finally we will get this 2k by n pi 1 minus cos n pi. So that is Bn. Okay. So Bn is non-zero, obviously, because if everything will go to zero, then what is the point of having a Fourier series? Anyway, so but we will see it for. So let's substitute this in Fourier series. So our Fourier series is f of x is equal to a was 0 and an was also 0. So finally we'll get bn only. So n going from 1 to n 1 to infinity, and we have bn. We are left with bn sine pi x by l, right? Sine n pi x by l. So you will get, you substitute bn, so you will get sigma n is equal to 1 to infinity. Bn is 2k by n pi and sine n pi x by l, right? So you will get this finally. So let's substitute n is equal to 1, 2, 3, and so on, and let's try to find out the series. And obviously here also L is pi, so it will convert into sine nx. So finally we will get. Okay. Now let's substitute n is equal to 1, 2, 3, and so on. So you'll get, so for n is equal to 1, you'll get 2k by pi, 1 minus cos pi is minus 1, so you'll get 2 again. So you'll get 4k by pi into sine x, right? So for n is equal to 2, for n is equal to 2, what you will get? So n is equal to 2 because cos of 2 pi is 1, 1 minus 1 will be 0. So all the odd terms will be, all the even terms will be 0. So when n will be even, this will go to 0 because this is 1. In case of cos of n pi, when n is even, this is 1 minus cos n pi will be 0. In case of odd terms only, it will be there. So let's say for n is equal to 3. So it will be 4k by 3 pi sine 3x. And then n is equal to 5. So you'll get 4k by 5 pi and sine 5x. And plus and so on. Okay, so this is our Fourier series that we have approximated, and this is corresponding to this function here, this rectangular uh, step function. Okay, not a step function, but it's varying between two steps. Yes, somebody wants to speak anything. So finally I'm denoting, so there is something known as partial sums. So the first partial sum is this. If we take only one term, so it is known as first partial sum. If we take two terms, then we have two partial sums. So sine 4k by pi sine nx plus 4k by 3 pi sine 3x. So this is known as second partial sum, and then we have third partial sum. So we have 4k by pi sine x plus 4k by 3 pi sine 3x plus. So this is third partial sum. Okay, so we just say that first partial sum, this is second partial sum, and here this is known as third partial sum. Okay, now let me plot this first partial sum, second partial sum, and third partial sums, and let's see how it approximates our main periodic function. So let me just do that. You can plot this on any graphing calculator as well. So you can just go on Google, type Desmos graphing calculator, and just try to plot this. Let me do this for you. So see if we can do this. I'm just sharing my screen. If you can see my desktop. So are you able to see this Desmos graphing calculator? So I'm going to plot first partial sum, second partial sum, and third partial sum. So first partial sum was y is equal to 4k by pi sin x. So I'm assuming that my k is 2. Okay, for the time being, let's assume k is 2. So 4k by pi will be 8 pi by sin x. 8 sin x by pi. So 8 into sin x divided by pi. Okay, so this is my uh, first partial sum, and if my k is 2, so then my function, original function will go from. So let me just plot that as well. Uh, Anyway, so let me just plot second partial sum. So for second partial sum is this first partial sum plus I have 4k by 3 pi. So k is 2. So 8 by 3 pi into sine 3x. So 8 into sine. Okay, graph is not visible. Let me just share again. Okay, sorry. Is this visible now? Is this visible now? Okay, so yeah, so I got your point. So then we have first partial sum, then second partial sum will be 4k by 3 pi, k is 2. So 8 sine 3x divided by 3 pi, right? 3 into pi. And then let's plot the third partial sum, y is equal to, and you can go on plotting partial sums. So you can fourth partial sum, fifth partial sum, there will be infinite number of terms. So I'm just plotting third partial sum. So it is 4k by 5 pi into sine 5x, and our k is 2. So then we have 8 into sine 5x divided by 5 pi. Okay. Now, what was our original function? It was minus k to k, right? So let me, if I am able to plot, let me just do that. So my function was y is equal to minus 2. Uh, I think we cannot put this. If uh, okay, y is equal to k for if x is 0 to, let me just try, okay, x is minus pi to 0. Is it happening? I think step functions, maybe I don't know how to plot step functions, but anyway, so our function was minus k to k, right? So if you see what is minus k line, so this minus 2 is minus k and 2 is plus k. And then we had 0 to pi. 0 to pi means 0 to 3.14. So approximately, yeah, so this is 0 to pi, right? And this is minus pi to 0. So when we had minus pi to 0, we had a value of minus 2. And when we had 0 to pi, we had a value of 2, right? And you see, if I plot the third partial sum, so you see how nicely my third partial sum is trying to approximate my periodic function. So although it was a rectangle, but now if you keep on taking, let's say you take 7 or 8 terms, it will almost look like a rectangle. So that's how Fourier series approximates your periodic functions. So let's try to include one more term here. Then we have 4k by 7 pi. So it will be 8 sine 7x divided by 7 pi. Now you see number of variations are increasing, and I'm telling you, if you take, let's say, 10 terms of this Fourier series, then your Fourier series will approximate very nicely this rectangular periodic function. Now, do you understand the, so one more thing, this rectangular periodic function was not differentiable also. At 0, it had a jump, right? So it will have a very sharp, it will not have any slope. But we have converted this into a function which is continuous and differentiable. That also is one of the advantages. Anyway, so I think this conveys this message. Let me share this class screen again. Okay. So I think now you would have understood the why we were doing all these things. So we were trying to approximate a periodic function with the help of sine and cosine terms. Anyway, so, and I would suggest you to do the same thing with Taylor series. Taylor series also approximate the functions. Let's say you plot one, we plot the sin x, and then you plot some number of terms in Taylor series. Then you will see that the Taylor series, the polynomial will try to approximate the sine curve, but up to a certain limit only. After that, it will diverge. But this Fourier transform will cover this periodic functions for x going from minus infinity to infinity. Anyway, so okay. Uh, then I would like to add two notes, then we will end the class. So first one is note 1. In the next class, in tomorrow, we'll do Fourier integral and Fourier transforms. Okay. Note. The first note is if f of x is even function, I think wait. It means f of minus x is equal to f of x, right? This is even function. Then we will be left with only Fourier series, Fourier cosine series. Sine term will go to zero. You can prove it very easily. I'm just not proving it. So if f of x is even function, then Fourier series reduces to Fourier cosine series. Why cosine? Why not sine? Because cosine of minus x is cosine x only, and sine of minus x is minus sine x. So in that way, it will go to zero, and only even function will exist. Even function is cosine function. So and a0 will also go to zero, and bn will also go to zero. You will be only left with an, and the series will reduce to f of x is equal to, sorry, a0 will not go to zero. Pardon, a0 will not go to zero. Only bn will go to zero. So series will reduce to a0 plus an, and now you have n is equal to 1 to infinity. An will come, right? So your Fourier series will reduce to Fourier cosine series, and now your an will be given by, because your cosine function is odd function, sorry, even function, so you can reduce that integral. So your an will be given by, so in your original function, your an was going from minus L to L, but since this is a even function, so then you can do some mathematics, and this will reduce to 0 to L. Okay, 0 to L, and this will also be twice here, 2 by L f of x cosine of n pi x by L dx. This will be your an, and the changes are, here we have 2 by L, and here it is going from 0 to L. 2 by L means it is something like on the left hand side of the x-axis and on the right hand side of the x-axis function will be similar. So uh, then you can just instead of integrating it from minus L to L, you can say that it is twice of 0 to L. Okay, so it's the same thing that we have done here. And then a0 will be given by, again, 1 by L. It will also go from 0 to L, f of x dx. Okay. Yeah, so initially it was 1 by 2 L, so it will also double, so it will be 1 by L, and initially it was going from minus L to L, now it will go from 0 to L. Okay. And when we have even when we have an odd function, so if f of x is an odd function, odd periodic and even periodic, obviously periodic should be there anyway, so odd, it means your f of minus x is equal to minus of f of x. Then the Fourier series reduces to Fourier sine series. So now your f of x will be given by n is equal to 1 to infinity bn sine n pi x by n. Okay, and then your bn will be, because a0 and an will go to 0, and bn will be given by 2 by L, 0 to L, f of x sine n pi x by L. Okay. So when your function is even function, your Fourier cosine series will reduce. Your Fourier series will reduce to Fourier cosine series, and it will have a0 and an, and a0 n will be given by these expressions. And when you have an odd function, so your Fourier series will reduce to Fourier sine series, because sine itself is an odd function, and it will be given by n is equal to 1 to infinity bn sine n pi x by L, where bn will be 2 by L 0 to L f of x sine n pi x by L into dx. So in the next class, we are going to start with Fourier integral, and we will deal with non-periodic functions as well. As of now, we have only dealt with periodic functions, but in the next class, we will continue with non-periodic functions as well. Okay, so we'll stop here for today. Do you have